In this final video, we're going to complete our static analysis of the patient holding their leg in that fully extended position. And as you can see here, we have most of our forces solved for. The last remaining force is our reaction force. And what I'm going to do here is I'm going to bring in some of the previous calculations and just put these numbers aside because they may come in handy. So note that we were able to calculate the resultant force going through the patellar tendon of 2,147 newtons. And it had two components, one that was 2,075 and the other was 566. And recall that we had an equation over here where this was the sum of our forces in the x direction, where we were left with two unknowns. But now we were able to solve for the x component of the patellar tendon force, and that was 2,075 newtons, and that was going in the negative direction. So we have a negative value indicated here. So we're going to add this negative to the negative 141, and that will give us the reaction force in the x direction. So now we have our equation with two unknowns down to one unknown. So we transpose our negatives to the other side, and we have a reaction force in the x direction, indicated here in the diagram, to be 2,216 newtons. Now we have our y component of our reaction force to account for. So what I've done here is I've taken the equation that was generated back on slide number 8, which is the sum of the forces in the y direction, and we had the same problem where we had one equation with two unique unknowns. But what we had just solved for in the previous video was the y component of the patellar tendon force, and I have that value over here on the upper left hand side of the slide. So I'm going to substitute that value in here, and that's going to be a positive 566. Recall that that's going in the positive y direction. And that gives our equation here, or that renders our equation with one unknown here. So we sum these values, transpose to the other side, and the mathematics gives us a value of negative 475.5 newtons. Now when we work through a static analysis and our final answer turns out to be a negative value, in this case it's in the y direction, that suggests to us directly that our original guess was wrong. Recall that I didn't know what the angle or the magnitude was for the resultant vector, so I had just simply guessed that it was at this point. And that meant that the y component was positive and the x component was positive. The x component turned out to be a positive value at the end, so that checks out. But however, our initial guess of a positive y was wrong because we have a negative value. So whenever we have a negative calculation, that means that our original guess was incorrect. The magnitude is correct, but our arrowhead should be on the other side. So what we're going to do here is we're going to make our correction for our reaction force. So we almost have our full free body diagram filled in. So recall that the x component of the reaction force was a positive 2216 newtons, was negative 475 newtons, and that would mean that it would be going in the negative direction while the x component is in the positive x direction, and they're drawn approximately to scale, not exactly to scale, but this makes the point here that these two perpendicular components would mean that our resultant reaction force would be directed in this manner. And that's our FR. So the last step here, or the second to last step, is to find the value for the resultant reaction force vector. And once again, we use Pythagoras' theorem, where we square the x component, we add that to the square of the y component. And so that's the 2216 squared plus the negative 475.5 squared. I didn't put the negative sign in here. That negative sign would be transformed to a positive anyways, but we run the math here, and we have a resultant reaction force of 2,266 newtons. What's left to determine is the angle of that resultant vector with respect to the horizon. And I'm going to use the tangent function. You could use the sine or cosine functions as well, but I'm going to use the tangent function here. And so the tangent function, where theta is the unknown, I know what the reaction force in the y direction is. That's the opposite. The x direction would be the length of the adjacent, so I have the 475.5 divided by 2216, and I can just work in the absolute values for this. And that would, to isolate the theta, that would be the inverse tangent of the quotient of these two force components, and that gives me a theta, or the angle for the resultant vector, of 12.1 degrees from the horizon. And so now I can finally complete my free body diagram, which is the solution to this problem. So when doing this, to make your final free body diagram, we always draw in the resultant vectors, not the component vectors. And so the resultant, and this was a given, of 150 newtons for our elastic band. Recall that we worked with the components because that was the process of the static analysis. There is only one component of the weight of the lower leg in the foot, and that's acting vertically downward. We determined our patellar tendon force is 2,147 newtons, and the reaction force vector is 2,266 newtons at an angle of 12.1 degrees from the horizon. So when solving a statics problem, this would be the final free body diagram that we would have to redraw from our first free body diagram. And one last point to note, that the reaction force magnitude is largely in response to the magnitude of the patellar tendon force. Even though the elastic band and the weight of the leg do play a factor in the determination and the magnitude and direction of the resultant vector for the reaction force acting at the joint, it is largely influenced by muscular action. So this ends our final video on our steps to carrying out a static analysis.